Hello everyone, thank you for joining today's webinar. I'm Sumit Singh, an electric motor expert at EMWorks. Today we are going to discuss about a switch reluctance motor. Here is the agenda. First, we will go through the advantage and disadvantage of switch reluctance motor and its working. Then we will see what are the design challenges for an electric motor design, and we'll go through the different solutions by EMWorks. Later, we will design a switch reluctance motor and we'll go through its electromagnetic analysis using EMWorks 2D and Motor Wizard tools. And later, I'll demonstrate you through the EMWorks 2D and Motor Wizard software. Switch reluctance motors is a simple machine. The stator and rotor are built through the punching the different lamination stacks together to form the core of the stator and rotor. Then we can wind the coils either directly on the tooth of the stator core, or we can wind them on the bobbin and then insert them into the stator tooth. We can use any standard frame of the induction motor to prototype or manufacture this switch reluctance motor. It is called switch reluctance motor because in nature either we have fluids, electric currents or magnetic fields. They all like to flow through the path of the least resistance, nothing but the least reluctance path, which means higher inductance. So that's the fundamental principle of working the switch reluctance motor. The reason we call it switched is that once the stator and rotor poles are aligned, then we quickly switch to the next phase so that the rotor keeps chasing the phase that is excited, and that is how the rotor continuously rotates. So here are some pros of switch reluctance motor. First, the construction is very simple. It does not consist of any permanent magnet embedded inside the rotor core. Second, it is very reliable and robust in nature. Third, since made up of the stack of laminations, that it has the capability to handle the high temperature. As discussed, there are no rare earth material used in the construction of switch reluctance motor. And the last, the end windings are very small since all the windings are tooth wound. But at the same time, we have some of the disadvantages for using switch reluctance motor. As we are not using magnetic materials inside the rotor core, it has a low power density. It has also a high torque ripple and noise, and also requires a very precise position feedback for control of different phases, excitation. The working principle of switch reluctance motor is very simple. Let us consider a piece of iron core as shown in the figure. If we excite this coil and the flux is flowing through this iron core, the iron piece will align with the minimum reluctance position and get locked magnetically. The same principle is followed in the switch reluctance motor. The minimum reluctance portion of the rotor tries to align itself with the stator magnetic field, hence the reluctance torque is developed in the rotor. The main concept is the reluctance of the magnetic circuit is depending upon the air gap. Hence, by changing the air gap between the rotor and stator, we can change the reluctance of the motor. It is very important to understand here is reluctance is nothing but a resistance to the magnetic flux, which opposes the magnetic flux. And for example, in electric circuit it is resistance, and magnetic circuit it is called reluctance. Let us consider the following notation for better understanding. We have a stator poles where A dash poles are for axis A phase, B dash poles axis for B phase, C and C dash axis for C phase, and similarly we have small a dash rotor poles axis for position 1, b and b dash rotor poles axis for position 2. Now the input is given to the A phase and other B phase and C phase neither maximum nor minimum. Then the stator pole axis A dash and the rotor pole axis small a dash are in alignment because the air gap between the stator and rotor is very less, and then minimum reluctance positions are compared with other poles. And we can see the torque is nothing but a derivative of the inductance and its position. So at this scenario the torque is equal to 0, where we can see the terminology. It's LA is represented for phase A inductance and theta is the angle of rotation. Now phase A will be turned off, as you can see in the scenario shown in the table. This was in the initial stage where the A phase was excited. Now we will turn off the A phase supply and the B phase is energized. Here the rotor rotates anti-clockwise, and even by changing the polarity of the motor we can easily reverse the motor. The torque develops since the reluctance changes from maximum to the minimum. The developed torque is equal to, as shown in this equation, 1/2 I square dl by d theta. The rotor movement is depending upon the number of poles. In our case, we get 30-degree rotation by energizing one phase at a time. Here torque is nothing but a rotor movement only. When the shaft reaches to position B dash, then there is no torque. Now the B phase will be turned off and the C phase will turn on. Then, as you can see in this picture, third scenario, then the torque is developed because of rotor axis A dash. Here A is aligned with the stator axis C and C dash. The rotor continues to rotate for another 30 degree. Then C will be turned off and A will be started. The motor operation continues until the input power supply. Here you can observe that the motor is rotating by self. Thus, switch reluctance motors are self-starting motors. So designing any kind of electric machine, either switch reluctance motor or synchronous reluctance motor, or is it a permanent assisted synchronous machines, is a challenging task as its electromagnetic, thermal and mechanical performances are coupled, and these all need to be taken care at the same time. Based on the design constraints and the design, the different choices and criteria has to be taken care of. So estimating these parameters and losses which generate heat in the motor and other factors such as back EMF, terminal voltage, current and magnetic flux linkages, magnitude, electromagnetic torque and cogging torques are the major challenges while designing any motor. Another characteristic of the motor is the high speed operation, that is mainly due to the flux weakening mode and due to its efficiency plot at different torque and speed. So determining the electromagnetic performance and also the structural deformation and stress caused on the stator and rotor due to magnetic forces is very important. So to make this design process simple and easier, EMWorks has various motor solution products. First, we have the Motor Wizard tool. It is a template-based motor design software that allows user to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic, and transient solvers equipped with integrated analytical and finite element based solvers. Second, we have the EMWorks 2D tool. It is a 2D magnetic simulation software that uses the finite element to solve magnetic, electric, and transient problems. EMWorks 2D allows you to study the effect of the geometric and simulation parameters changes on the design. It also allows to couple a transient magnetic study to mechanical motion and thermal. Third, we have the EMS tool. It enables users to do both electric and magnetic simulations using the complete 3D geometry. EMS is a true multiphysics software that enables users to couple the magnetic and electric design to circuit, motion, thermal, and structural analysis on the same model in a hassle-free integrated environment. So we will use these tools to design our switch reluctance motor topology. So here is the specification for this switch reluctance motor, and on the right hand side we can see its mesh diagram. So for today's analysis we have considered an 8 stator pole and 6 rotor poles configuration. The base speed is set to 2000 revolution per minute, and also the phase current peak is set to 200 ampere. The core materials used for stator and rotor core is M27 with 0.47 mm lamination thickness, and the conductors used are made up of copper materials. The rated power obtained is close to 10 kilowatt, and exactly it is like 9.64 kilowatt, and the average torque is around 46 Newton meter. So before moving on to the results section, let us quickly see what are the different model settings used in the EMWorks 2D software. So once we have a SolidWorks platform and the EMWorks 2D launched using the tool option, the first thing is to set the materials of the motors. We can go through the material database available in the EMWorks 2D, where you can choose the material as per your requirement, whether you need a linear magnetic materials or non-linear magnetic materials, different kinds of permanent magnets. Next is to set the boundary condition, where we will consider an outer ring as an air material to set the boundary for the analysis of the SRM motor. Third is to set the torque, where we select the rotor rotating parts, phases, and select the compute torque to set the torque calculation. Next is the mesh control, where user can select the different parts of the motor and set the control parameters for the mesh. And then last we have the winding settings, where user can choose whether a current driven or voltage driven coils, and then easily set the current amplitude and frequency, and also can import the current waveform of its own choice to run or to drive the motor topology in the EMWorks 2D software. So once we have done with all these settings, we run the analysis and then see the different types of results which are available in the result tabs. So let's move on to the result section, starting with static analysis, and we will also see the results obtained from EMWorks 2D, and at the same time we will see from the motor wizard tools also. Since due to the silency of stator and rotor, inductance is a function of rotor position in case of switch reluctance motor. So it is very important to visualize the inductance versus rotor position. So let us look at the results. Here all the waveforms are plotted for the half electrical cycle. So this is a position where the rotor pole and the stator pole are aligned and considered as the initial position. Since the reluctance at that position is very least, we get a very high inductance value. And as the rotor starts moving towards the unaligned position, and once the rotor reach its unaligned position, we get the very high reluctance and the least inductance value. Also, the result obtained in the Motor Wizard tool is very similar as we obtained in EMWorks study for inductance versus rotor position. Second, we have a torque versus rotor position where only phase A is excited at a time. When the rotor poles are aligned with the stator poles and A phase is excited, the torque is 0. And as the rotor starts moving away from the alignment, the torque starts increasing and then again come back to the 0, and similarly further it increases again and reduces to 0. The result obtained from either of the softwares are very similar. Next, in static analysis, we have the flux linkage versus rotor position. Similarly, as the rotor is when aligned, we have the highest flux linkage, and at the unaligned position we get the least flux linkage. Also, using these tools you can get the energy versus rotor position for switch reluctance motor. So let's move on to the on-load analysis using EMWorks 2D software. As we excite the phases step by step, so we have used an 8-pole and 6-pole configuration for stator and rotor. So here we have a phase A excited, and then once the phase A excitation is turned off, then we have for the phase B, then similarly for phase C, and then similarly for the phase D. The flux linkage obtained using this software is also very similar, as the current excitations were given to different phases. First, we have a flux linkage due to phase A excitation in green color, then followed by the B phase shown in red color, and then due to the C phase excitation, and then finally we have a flux linkage due to the D phase excitation. We can also obtain its electromagnetic torque, and here we can see there are very huge ripples which can be optimized, designed, and using the skewing technique. The average torque obtained is close to 46 Newton meter. Next, we have the flux and vector plots. So as we can see in this flux plot, when phase A is excited, the other phases B, C, and D are not excited, and all the flux flows from the rotor to the stator core and flows through its back iron and again enters the rotor core through air gap. Similarly, we can also obtain its vector plots to understand its working principle. Next, using Motor Wizard tool, we have obtained its torque versus speed performance. We can also obtain the different kind of analysis such as current versus speed and efficiency using the Motor Wizard tool. So to summarize, today we have simulated a switch reluctance motor, and we chose its outer diameter as 94 mm with stack length of 100 mm. The current rating of 200 ampere results into the average torque production of 46 Nm. The motor volume was calculated, and the torque density comes around 66 kN per meter cube, and the power density is as shown in the table. Now I would like to demonstrate you the simulation of switch reluctance motor using EMWorks 2D software. First is to set the materials for the different parts of the motor. So here we can see for rotor component I have selected M27 type grade of electric steel with 0.47 millimeter as a lamination thickness. Also for the same for the stator core. For our stator windings, we have chosen copper as a material to define the stator conductors. Then for the rotor shaft, we have chosen stainless steel material. So that's how we set the material for different parts of the rotor geometry. We can even select the material, we can even edit the material properties, and you can see once we click on the apply material, we get a long list of different types of material database from where users can select the materials as per their requirement. Then we set the load resistance, which is nothing but a magnetic vector potential around the motor, and we chose it as an air material. Then we set the force torque, where we need to select all the parts of the rotor cores or the parts which are rotating and where the torque need to be computed. Next step is to set the mesh of the geometry. As we can see here, even user can select the different part of the geometry and can control the mesh element and the size of the mesh they are interested. And then comes the winding setting. So here, as you can see, for A phase winding we have selected the slots, and then for similarly the next slots represent for B phase winding, and similarly for C phase windings, as you can see on the model. And finally, since it's a 4-phase design, so we have also selected the D phase winding. Once the simulation is run and completed, we can click on the result table to view all the results. Here users can see different types of results. For example, torque, which we need to add to the parameters, and using the plot preview option we can see the torque results. So here is the electromagnetic torque for switch reluctance motor. We can even click on the pop-up plot to get more detailed magnitude of the torque plot. So click on the listing where you can see time versus torque magnitude. Next we will see the inductance, where users can get the magnitude of self inductance as well as the mutual inductance magnitude for all the 4 phases. Then we can see the flux linkage. We can add all the phases, and here we have the results for the flux linkage for A phase, B phase, C phase and D phase respectively. Next, let's look at the magnetic flux density, where I have chosen the plot format as fringe, and you can choose the overlayer as mesh, contour lines or vector. So let's select the mesh and view the result. So within few seconds we have our results, where we can see the magnetic flux density with combination of mesh, and let's see its animation plotted with respect to time. So as we can see the status, it's loading data, and since it's an animation which runs all these steps and show the magnetic flux density variation, so it take little bit time, and then once it's done you can see the. So first we are excited. At this moment you can see that B phase is excited, and then it switches to C phase to keep the rotor rotating, and then finally it switches to D phase winding and D phase is activated. So that's how we can see the working of the switch reluctance motor, and we can also see its applied current density, magnetic vector potential and many more. So in today's webinar, a switch reluctance motor topology was simulated, and we saw its electromagnetic as well performance using our EMWorks 2D and Motor Wizard software. It was also observed that the switch reluctance motor can be the alternative solution to fulfill the growing demand of the electric vehicles, and since it do not require or do not have a dependency on the permanent magnets, I think it can be one of the viable solution which will replace the permanent magnet synchronous machines and also lead to a lower prototyping cost for electric machine. However, in nutshell, the selection of motor topology is basically a trade-off between the constraints and what kind of performance we need from the electric vehicles. If we need a high power density or high torque density motor, then we obviously need a permanent magnet type of motor design. But where the performance is also a factor, as well as the cost is the factor of the machine, then in that case switch reluctance motor becomes one of the best solution. So here are the references for our today's webinar. Thank you so much for attending the webinar today, and I request all the participants to please use our chat box option to ask your questions. Thank you so much. See you in the next webinar.